So this is where we stopped in the previous video, the equation for 1D, continuity equation for 1D, continuity equation for 3D, but of course we've substituted Darcy equation. And so we're going to move back to the simpler one for 1D, because we know whatever we do for 1D, it's easy to generalize for 3D, right? You basically just repeat this same form, but in the in the Y and Z directions. So what we're going to do is to simplify this equation under certain assumptions, assuming some of the terms are constant. So I'll start out by writing that equation here for 1D, and it's d dx of what? Rho k over mu coming from, so this is pressure, not density. And this is density. So this is what you have. It's equal to what? The derivative with respect to time of phi rho. So we're going to make some assumptions that permeability, viscosity, and porosity are constant, but density isn't constant, right? So these terms are constant. Sorry. So this, and this. Why do I keep selecting the wrong one? And this, right? So porosity, viscosity, and permeability. So because these guys are constant with respect to space and time, so I should say they are constant with respect to space and time. Space and time. So with respect to x, with respect to t, they are constant. And so you can take them out. So k over mu, or the derivative. And you're left with this, the p dx equals, phi is constant with respect to time, right? And you have the rho, the t. So the next thing we do is to focus on this term. And the question is, how do you differentiate that term? How do you differentiate what's in the bracket with respect to space? We use a rule in calculus. Which rule do we use? Product rule, right? How do you differentiate with respect to x the product of u and v? It's u dv dx, right, plus v the u dx. And that's what we're going to use to differentiate this term, so that that term becomes, it's going to come to it here, it becomes what? K over mu. I just ignore that for a minute and focus on the derivative. So we keep rho and differentiate with respect to x the p dx, right? That's what this one says. Then we keep the other term, which is the p dx, and differentiate rho with respect to x. And what does this give you? It gives you rho, this is second order derivative, right? The 2p dx squared plus the rho dx dp dx. And that's pretty much what this is. See that? What about the k over mu that was outside? Right here. We can multiply both sides by mu over k so that this goes away, and that's why you have mu over k here, right? So k over mu originally, this is the term we derived, multiply both sides by mu over k, and now you have phi mu over k on the right hand side, right? So you have phi mu over k on the right hand side multiplied by phi the rho dt, which is what we had before. So that gets us to equation 2, right? And now we want to simplify further. And the terms we want to simplify further are these derivatives. The rho dx, the rho dt, the time and spatial derivative of density, or better still, the derivative of density with respect to space and time. So for that, we're going to introduce the concept of fluid compressibility, which is minus 1 over v dv dp. That's the density, the definition for fluid compressibility, which you should have learned in your fluid properties class, right? And now we want to simplify v, and we're going to use its relationship with mass and volume, with mass and density, I mean, because density is mass per unit volume. So volume, make volume the subject of the equation, is mass divided by density. And if we differentiate this volume with respect to pressure, what do we have? We provide the equation for density, for volume. So differentiate volume with respect to pressure is same as differentiating m over rho with respect to pressure. So this is you differentiating volume, which is mass per unit, or mass divided by density divided by pressure. You're differentiating it with respect to pressure. And mass is going to be constant with respect to pressure, right? The mass is conserved. Mass doesn't change. So you take the mass out, right? And you're left with 1 over rho dp. So that's what we're doing. We're differentiating 1 over rho with respect to pressure here. And how do you differentiate 1 over rho with respect to pressure? You can use chain rule, and that's what we're doing here. So d the rho of whatever you're trying to differentiate times the rho dp. All right. Same thing as the y dx equals, that's chain rule, equals the y du times the u dx. That's just calculus. And that's what we're doing here. So the 1 over rho, the rho dp. So the rho here, the rho here, the u here, the u here, same deal. And that gives us this. And now we move on to dv dp. I mean, same thing here, but we're just working more on the right hand side. So what's the derivative of 1 over rho? The rho. It's minus 1 over rho squared. How do I know that? Another rule in differentiation from calculus. What's quotient rule? So quotient rule says if you're going to differentiate, say u over v, you want to differentiate u over v with respect to x. You use v du dx minus u dv dx, all right, divided by v squared. And if you set u to 1 and rho to v in this equation, this is precisely what you get. I'll let you do that since this is basic calculus, right? So you do that and you have minus 1 over rho squared, the rho dp. And now we can substitute this in CF, which is equation star. So this is our fluid compressibility, and we have an expression for the VDP, which is precisely this. So in place of the VDP, plug in this term here. Let it replace this. And what you have is CF equals this. Right? The minus here cancels out the minus here. And now you have rho over m over rho squared, which is what this is, the rho dp. Where did rho over m come from? 1 over v. because V is rho over M, right? So it becomes, what did we already did all of that here. V is M over rho. V is M over rho, so 1 over V is rho over M, the inverse. And that's what this is. And then you see rho cancels rho squared, you're left with rho. Mass cancels mass, that goes out, and the only thing left is the rho dp. So that's how you get your fluid compressibility as 1 over rho d rho dp, which is similar to the original form, was minus 1 over v dv dp. Different ways of writing the same equation. And then we can use chain rule on the rho dp. We've talked about chain rule before, right? This is chain rule. Use that on the rho dp, and the rho dp becomes the rho dx dp, right? Precisely chain rule. And you know that dx dp is inverse of the p dx. That's what I'm showing here, so that you can actually multiply both sides by dp dx, and then cf times dp dx will be equal to this, right? So cf times dp dx equals that. And we can also multiply both sides by rho. This becomes rho cf times dp dx, right, equals the rho dx. And that's how we get this. Can use the same chain rule, but instead of differentiating with respect to x, right, we'll differentiate with respect to time. So this becomes the rho d time, the rho dt, then the t dp, right? Another way of using chain rule, but with respect to time instead of being with respect to x, and that's what you get here. The rho dt, the t dp. And multiply both sides by, so this dt dp is same thing as 1 over the p dt, right? Just taking the inverse. So you can multiply both sides by dp dt times rho to give you rho dp dt times cf, and you're left with only this term because this goes away. And now you have expressions for the rho dx, the rho dt, the derivative of density with respect to space and with respect to time. These two terms show up in the governing equation, equation 2. And we are going to, instead of writing the rho dt, we will write this. Instead of writing the rho dx, we will substitute this into equation 2. And for your reference, this is equation 2 once again. That's the rho dt, which we're going to replace with what we just derived. And this is the rho dx, which we're going to replace with what we just derived. And so the equation becomes this. So that's the term we just substituted in. This is the second term we just substituted in. So this is this. And that's same equation as before. And now you see that density is showing up on each side, and it's not within the derivatives anymore. It's outside. So you can cancel out these densities. And this is CF, the PDX squared, right? The PDX times the PDX squared. This is what is left of that term. This is what is left of the right-hand side. And because the PDX is a small number, when you square a small number, it becomes even much smaller. And so it becomes negligible. And because of that, we can neglect the first term. And we are left with the second order derivative of pressure with respect to x. And the right-hand side remains the same. So we're left with this. And that's our simplified form of the equation, which you'll see in your lecture notes. And the assumption to simplify the equation to this form is that phi, mu, and k are constant. We don't assume density is constant. We go through these derivations and eventually density just falls out of the equation. And this is the diffusivity equation which we use in well testing, pressure transient analysis. This is the equation we used. And again, these are the assumptions we had to make for this equation to apply. But in reservoir simulation, we do not make these simplifying assumptions. We leave the phi, mu, and k in there, also the density in there, and we solve the non-linear system of equations numerically. This is the equation in 1D, right? You can also write this in 3D. How will you write it in 3D? Basically, add more terms here. So I'm going to rewrite this here. It's going to be the 2p dx squared, right? Plus the 2p dy squared plus the 2p dz squared. Right, that's all you need to do to write it in 3D form. In radial form, this is what it looks like. It's the 2p dr squared plus 1 over r. The p dr right hand side remains the same. This is k. This was kx. This is k in the radial direction. Permeability in this direction. That's the radial direction. Good. So again, that's the equation we solve in well testing. It's called the diffusivity equation. You've seen what we had to do to get this form of the diffusivity equation. We basically assume these terms were constant, and we did simplify it.